Radiation waves. Something that is very hot, you'll get burnt. This is because of conduction. The heat is conducted by a sort of domino effect from molecule to molecule, or from atom to atom, along the hot object and into your fingers. That's one kind of heat transfer. But if you hold your other hand above the same hot object, you will also get burnt. This is because of convection. The hot object causes the molecules of air above it to speed up. The hot air expands and becomes less dense, and is therefore conveyed upwards. That's a second kind of heat transfer. Are these the only two ways that heat can be transferred? Then why are you sitting under that beach umbrella? Because the sun's too hot? But how can the sun transfer heat to you? You're not touching it, so there can't be any conduction, can there? And since most of the space between you and the sun is just that, space, except for the thin layer of air formed by the Earth's atmosphere, there can't be any convection either, can there? Because once you get beyond our atmosphere, there's almost nothing out there to do the convecting. But the sun still feels hot. Amazing. How is that possible? Is there a third kind of heat transfer which allows heat to move through empty space? Yes, there is. And to understand it, you must first of all remember that heat is a form of energy. Now, energy can travel in various ways, but one of the chief ways in which heat energy travels is in the form of waves. Rather like the waves that a boat makes when it moves through the sea, or the waves that spread out when you drop a pebble into a pool of water, or the waves that travel along a rope if you jiggle one end of it up and down. In all these cases, what you are seeing is the effect of the movement of energy itself. By means of waves, energy can move through any distance. You can do it yourself. You can make that umbrella move without touching it. Tie one end of your rope to the umbrella, and now move your end of the rope up and down. You can actually see that your energy is traveling through the space between you and the umbrella, and then making the umbrella move. The heat energy from the sun travels like that. The sun sends out waves of heat energy in all directions. Each of them is rather like the spoke of a wheel, and this is exactly what scientists call them, only they use the Latin word for spoke, which is radius, from which they get the word radiation, the name given to this third kind of heat transfer. So it's by means of radiation waves that the sun can transfer its heat energy to you and make your molecules go faster and therefore make you hotter, even though the sun is millions of miles away. Just as by means of waves again, you can transfer your energy to the umbrella and make it move, even though you're standing several meters away from it. But it isn't just the sun that radiates heat in all directions. So does an ordinary fire, or a stove, or an electric light bulb. In fact, waves of heat energy are radiated to some extent by all sources of heat. Even you radiate a certain amount of heat in the form of waves. Come to think of it, there are waves everywhere. Oh, watch out. Here comes a big one now.
Most waves have to travel in a medium. Right? Water waves travel in water, sound waves travel in air. They need something to carry them along. That's what's so great about the EM waves. They don't need a medium, which again I pointed out was really good, or else we wouldn't be able to see the sun. Okay, so how do these EM radiation waves actually work? A little bit of chemistry. Atoms are made up of protons and electrons. Protons are positive, electrons are negative. And the way the atoms work is the hotter they are, the more they vibrate. The more they vibrate, the more excitement, the bigger the charge. Okay? Like charges repel each other, unlike charges attract. But as the atom itself gets more and more vibration, the difference in the vibration from its original state to either more or less can be felt by the other atoms. And even though they could be like a light year apart, the difference can actually be felt. Not exact difference. And so that's what creates EM field and allows the EM radiation to travel throughout space. Now, a lot of people think, oh, waves go in one direction, right? Well, not quite. If you drop a pebble into a pond, right, the wave doesn't just go to the left or to the right or up or down, right? It goes in all of those directions. So the electric field is actually generated in all directions. So this is just a summary of what I had said. Charged particles are constantly moving. When it heats up, it goes faster. The electric field will start moving and vibrating, causes the electric force to be felt by other charges, no matter how far the distance. Obviously, the closer you are, the more you're going to feel it. And then the information about these particles are transmitted through space via the changing electric field. So we call it EM radiation or EM fields. Why is this? Well, because they kind of go hand in hand. Electric fields can generate magnetic fields. And so the change in an electric field will cause a change in the magnetic field. Same idea. Felt over a distance, attract, repel. Closer you are from the source, they're going to be felt. Okay, so that's how waves work. Great. Why can we see them? Right? We see light, which is a wave. Why can we see it? Well, everything has a temperature, right? So it's vibrating at a certain amount. And those atoms, protons, electrons, molecules, whatever you want to call them, they're vibrating and they can sense the change. They can create the field, right? Now these travel all the way from, let's say, the sun, all the way to us, and our eyes are actually picking up the waves. The visible waves, granted, but the waves. And that's what's happening. Our eyes can actually pick up the field, and that's what we're seeing. If you want more biology than that, then go take physics or biology. Okay, so how fast can these things actually travel? All of them, all of the EM radiation, travel at the same speed, the speed of light, which again is denoted as the letter C, or 300,000 kilometers per second.